A very good afternoon to everyone. This is Shubhangi Rao and I am working as an assistant professor at MLR Institute of Technology. Today we are going to discuss about continuity equation and relaxation time. So let's start. So before going to the diagram, let's discuss few points about electric charges. As per the law of conservation of electric charges can neither be created nor destroyed. So, to justify this, to understand this concept, we are going to consider a volume V which is bounded by a surface S. Volume V which is bounded by a surface. Also, we will consider the net charge Q in exists within the region. Now, if a net current I flows across the surface, the charge in the volume must decrease at the rate that equals the current. If a net current flows across the surface into the volume, the charge in the volume must increase at the rate which is equal to the current. So, as we say in the first point that electric charges can neither be created nor destroyed, means equal amount of positive and negative charges must be there. So, what we can say by this concept that the current leaving the volume in the total outward flux, the current leaving the volume is the total outward flux of the current density vector through surface S, and this can be written in the form of equation I out is equals to integration of J dot ds is equals to minus dq in by dt. Out current, in current, positive, negative, equal numbers are there. Now here we can use divergence theorem which says integration of J dot ds is equals to divergence of J dv. So as per divergence theorem, the surface integration of any vector is equals to volume integration of divergence of the same vector. So here we have applied divergence theorem and as per that we get this equation. Further solving it, we get minus dq in by dt is equals to minus d by dt integration of rho v dv, which can also be written as minus volume integration of dou rho v by dt. Now we substitute this 2 and 3 in equation number 1 and we further get integration of divergence of J dv is equals to minus integration of v dou rho v by dou t, and further solving it we get divergence of J is equals to minus dou rho v by dt, and this equation is called continuity of current equation, or in simple language we can call it continuity equation also. So basically we can say, or it states that there can be no accumulation of charge at any point. Also we can say that for steady currents dou rho v upon dou t is equals to 0 means divergence of J is equals to 0. Also we can say the total current leaving a volume is same as total current entering it. So basically it follows Kirchhoff's current law. Now we have to discuss about relaxation time also. So we discuss few points that if we introduce charge at some interior point of a given material with constant sigma and epsilon, then its effect can be obtained using continuity equation. So as we know, the Ohm's law J is equals to, this is a point form of Ohm's law J is equals to sigma E, and also we know the Gauss law says divergence of D is equals to rho V, and we can write divergence of E is equals to rho V upon epsilon because in place of D we are putting epsilon E. Now we are substituting in the continuity equation, we get divergence of J is equals to minus dou rho V upon dou t. In place of J we are putting sigma E, and this is as it is. We are further solving it, we get sigma rho V upon epsilon is equals to minus dou rho V upon dt. We simplify, we rearrange it and we get dou rho V upon dou t plus sigma upon E rho V is equals to 0. This equation is a homogeneous linear ordinary differential equation. Now if we separate the variable, we get dou rho V upon rho V is equals to minus sigma upon epsilon dt. Now if we integrate both the side, we get ln rho V is equals to minus sigma t upon epsilon plus ln rho v naught, where this rho v naught is the constant of integration. So we get rho v is equals to rho v naught e to the power minus t upon tr, where this tr is equals to epsilon upon sigma, right? So this is the equation which we are getting, rho v is equals to rho v naught e to the power minus t upon tr. Okay. So there are a few more points to discuss here, that when we introduce the volume charge density at an interior point in the material, it decays and it is resulting in a charge movement from the interior point at which it was introduced to the surface of the material. The time constant Tr of this decay is called relaxation time or rearrangement time. So if we want to define relaxation time, we can say it is the time it takes for a charge placed in the interior of the material to drop to e to the power minus or 36.8% of its initial value. And it is very short for good conductors and it will be very long for good dielectrics. For a good conductor, the relaxation time is too short that most of the charges will vanish from the interior point and they will appear at the surface within a short time because the period is very short. For good dielectric, the relaxation time is very long that the introduced charge remains at the same point because of the too long time, right? The value of relaxation time for these materials are given here, right? So this was about current continuity equation and relaxation time. Thank you very much. I hope it is clear and helpful to you all. In case of any query, please write to us. Thank you very much once again.